Everybody, we'll get started right here. I was like, oh, I got the long intro plan. I was like, oh, we'll just get started. We'll get going. We got our coffee. We're waking up. Happy Monday, Miranda. Good to see you. What questions are there? How is everyone doing? Hmm. We should start with our what's going on this week in 201 through 20. My gosh, we had so many tests last week. Woo! How are people doing? What questions are there? I am just it's nice that we can good to see you here, Maddie. Also, it's good to have a weekend, good to just relax. Oh man, we had such a good weekend. I hope everyone did too. But man, we had some ham yesterday. Oh man, just getting to cook some good food. Anyone else have some good food yesterday? Good food, just relax, have a good weekend. You bet. Chapter 14 homework. Let's do it. Let me get my Pearson pulled up. Got to relax. Let's see right here, my Pearson. Who had good food yesterday? But we didn't get to see family, though. We're all the way in Texas, and family's all the way in Tennessee, North Virginia. So far away. Let's see here. Chapter 14. Almost got it up. Did you say, I think you said the homework, right? Did we go over a new unit? We've started chapter 14. Yep. So we've started chapter 14. I was traveling during the Wednesday class. What did I miss? We started chapter 14. Yep. So chapter 14 homework. Let's go right here. Sampling distribution of the sample mean. This is the new information. So let's get the homework up and going. Okay. Here we go. New homework. So let's check this out. Let's check out the new homework. About a bunch of threads, and I'm teaching myself how to embroider. Maddie, you're working with metal last time, right? So you're working with metal. Now you're teaching how to embroider. Gosh, that's some awesome skill sets. Keep it up. Keep learning, keep practicing, keep new skills. New skills. It's kind of like a video game where you get skills and you level up. So keep doing that in life. Keep getting those skills. Let's hop over to the main screen. Okay, here we are. So this one is about weighting tables. A waiter believes that their distribution of tips has a slightly left skew with a mean of 10.6. I made a crown of vinyls and oh, that's awesome. So I had a standard deviation. So let's go ahead and copy our problem right here. So we're going to copy the problem. There we go. And bring it over here to Word. And we need to immediately mark these things. So what are we going to immediately mark right here? Any ideas for any of these? We're taking pictures. Oh, cool. Yeah, awesome. That'd be great to see. What do we have right here? What do we have? Sorry, hiccup right there. What information is there in this problem so far? What information do we have? So we always pause and we try to figure out the notation. We can also check the conditions. These need to be randomly selected tables, 10%, randomly selected. They need to be less than 10% of all tables, and then they need to pass the nearly normal condition, which is going to be nearly normal large enough. Which, do I have those notes up? Ah, we do. Here's the nearly normal large enough. We can see here 1, 25, 100, and they're taking a sample size of 30. And they said slightly skewed. So let's highlight the condition with orange. So slightly left skewed, and we do pass the condition then. They don't have you check the condition, but this would be slightly skewed, so you need at least 25. That's marking through it. But we'd be using this right here, and we have at least 25. So is our sample size large enough? It is, exactly. And so we do have all this information right here. Let's go ahead and mark it. And this is where sometimes some mistakes are made. Mistakes were made. Because right here, this is going to be the true mean, and this is going to be the true standard deviation. And this will be the sample size, lowercase n right here. And this is an observed mean. So, or they haven't done the mean yet. We haven't done that yet. That's an amount. And we want to figure out over 30 tables making $350. So how would we, with making $350 over 30 tables, figure out how much we want to make on average? Because they're saying, over the weekend, I'd like to make $350. I have 30 tables to make this on. So they have 30 tables to make this on, and they want to make $350. So think about what we would do with they want to make $350 and they have 30 tables to make that on. So you'd say, how much do I need to make on average per 30 for my 30 tables? And you would take your 350 right here and you would divide by 30. So this is going to get us on average how much they have to make. Now when I enter this in, so this is the average tip they need to make. I'm going to enter in a bunch of 6s because we need to carry the decimals. So we're going to do a whole bunch of 6s right there. Okay, so with this right here, we have the mean, the standard deviation, all this good stuff. Hey, good to see you here, Caitlin. So now we need to draw the sampling distribution. This is where people usually get stuck, is we know that the mean for the distribution of sample mean y is equal to the mean. And the standard deviation for the distribution of the sample mean y is equal to the original standard deviation over the square root of n. And so now we're just going to plug in the numbers. Well, the mean's equal to the mean, so it's equal to 10.60. The standard deviation is equal to the standard deviation over the square root of n. So we need to take the original standard deviation of 5.60 and divide it by the square root of 30. It's going to be about 0.9 or so, 0.9, something like that. So 30 square root. It's going to be more than 0.9 now. Oh, no. Got to watch out. Typos will get you. 1.022. So this is the new standard deviation. And the distribution of the sample mean will always be what-er. Like, look at the new standard deviation versus the old one. The new standard deviation right here versus the old original standard deviation. The new standard deviation, part of the central limit theorem, says that this curve will always be what to the old one. The old one right there is also shaded, but here's the new standard deviation. This is one of the key aspects of the central limit theorem, is that the new curve will be what-er. And let's kind of talk over the central limit theorem here. I'm going to bring up central limit theorem applet. There it is, central limit theorem applet. That's not it. Here it is. And so the central limit theorem applet states, if we have a skewed distribution, which this says it is, and we do sample sizes of, this one says 30, but we don't have a 30 button on this. If we do samples of 30, we're going to be averaging together 30 tips. Exactly, tighter and more normal. And tighter was what I was looking for, Zoya. Great job. Let's throw out some points we haven't this morning yet. Zoya, you're exactly right that the standard deviation will be smaller, i.e. tighter. Yeah, let me post the link for the applet. Here's the applet. Whoops. There we go. There's the applet link right there. And so what we're doing is we're taking samples of size 25, like we're doing our samples of 30, and we're getting a blue dot down here, which is the average of these. If we continue this process a whole bunch, we will get a distribution of the sample mean. So this is what we're actually drawing right here. This mean right here is this mean right here, which is the same mean as the top one. It's the same mean. If we do more simulations, we'll get 8.08, and that's the same mean. This standard deviation right here of 1.25, so the standard deviation is going to be the square root, or this divided by the square root. So we take 6.22 divided by the square root of 25. So square root of 25 is 5, and there you go, 1.244. And probably if I do more simulations, this right here will go to 1.244. There we go. You see it's so close. There's a bunch of decimals in the background. We just got to do tons and tons. I don't want it to say 1.25. Oh my gosh. Wow, it's so close. It's just like, I'm waiting for it to eventually go down to 1.244. Come on, theory. I have a feeling if I do it long enough, it will do it, but we might be here all day. It's going to drive me nuts if it doesn't say 1.24. I'll come back to this later on. Wow. Theory should work. I wonder what this is actually right here. The standard deviation might have more decimals. Maybe there's more decimals we can't see, because if that's 1.224 or 6.224, yeah, then there might be enough decimals there that's barely hiding out. Oh, man, I want to say 1.24, I swear. Anyways, wait, how did you enter the data in the applet? Oh, so the applet doesn't have you enter in the data. The applet just shows you what would happen. So we're not going to use this applet right here. We're just using it to understand what's going on. So do you see these green numbers right here? Like, these aren't the same numbers, but these green numbers are the mean and the standard deviation for the original distribution. And the original distribution is skewed, right? So you see, if you look at the very top, you've got a mean and a standard deviation for the original distribution. Does that make sense? Like, here's the mean, here's the standard deviation for the original distribution. That's these green numbers up here. That's these numbers, the mean and the standard deviation. But the new distribution, the distribution of the sample mean of size 30, has a different mean and a different standard deviation. Well, it's the same mean, but it has its own mean, which is the mean, and it has its own standard deviation, which is the new standard deviation divided by the square root of 30, and that's down here. And this is the new distribution that is tighter and more normal with the same mean, because it's mu, and the standard deviation is the original standard deviation divided by the square root of the sample size. In this case, we're dividing by the square root of 25. Does that make sense how we go from the original distribution up here, which are the numbers in green? Here's the original data for the mean and the standard deviation. We then take the mean and the standard deviation and get the new mean for the distribution of the sample mean and the new standard deviation for the distribution of the sample mean, and that's what we're seeing down here. These are the numbers highlighted in blue because they're the new mean for the distribution of the sample mean, the new standard deviation for the distribution of the sample mean highlighted in blue, and the only one that changes is the standard deviation. The mean stays the same. The mean is still the same. You can see the mean right there. So they can get tighter, but they keeps the same mean. The mean up here is 8.08, and the mean down here is 8.08, and then the standard deviation down here is smaller, and it's more normal, which is the two things of the central limit theorem. So we're reviewing the central limit theorem by saying the new distribution of the sample mean will be more tighter and more normal. And when is it normal enough? Here's the review on passing if it's normal enough. We need quantitative data. If it's normal, the sample size only needs to be 1. If it's skewed, the sample size needs to be 25. If it's heavily skewed, 100. And we check to see, based on the shape, if we have a large enough sample size. This problem says that it's slightly skewed to the left, technically. And since we have a sample size of 30, that would be large enough. Slightly skewed would be somewhere here. We need at least 25. Our sample size is 30, so we're larger than that. We pass it. Does that make sense? How to pass the nearly normal large enough condition? We're doing like additional things here to make sure we understand the theory behind this problem, not just solving it. So we do have the conditions met, and if we meet the conditions, this is what it means. It means that we will get a distribution that looks like this, which is nearly normal. So we can now use the normal techniques on it. So we're going to do awesome. Great job, Maddie. And so now that we know we meet these conditions, we're just going to take these numbers right here. We're going to talk to Mr. David M. Lane. So MuBot's going to get David M. Lane pulled up for us. But all we're going to do is just draw these numbers in. We could write them down, but David M. Lane's going to help out a lot more by just drawing it for us. Like sometimes people use Z tables and stuff, but I prefer David M. Lane. It's way easier. Here we go. MuBot brought up David M. Lane. Thank you, MuBot. And so we'll go right here to David M. Lane. I think what was the mean again? 10.06. 10.60 and 1. There's the standard deviation. So now you see we have the mean and the standard deviation in here. And now we want to see the probability of making an average tip above 11.66666666. So we go above 11.666666. And if you're wondering how we got that, that was obtained by finding out with $350 that we want to get over 30 tables. So this was, we'll write this in green right here. $350 is what we want to get over 30 tables, and that is how we obtain that number. Now, I don't know if we can see the answer yet, but this is a good test question. If a test had the possible answers 18%, 15%, 4%, for explaining high leverage, do you just compare the x values or the unusual row to mean? Yep. For high leverage, compare the unusual x's. Great job right there, HDT. Yep. Compare the unusual x's for high leverage. Great question. What do people think the p-value for this will be? What do you think the probability of this will be? 18%, 15%, or 10%? And look right where it's at. It's right here, right above 1 standard deviation. So with it being right above 1 standard deviation, it's going to be right about 15%. Let's scroll down. Right about 15%. And this is why knowing the empirical rule is a huge help. If you run into a problem like this, you can be like, it's about 15%. You don't even need David M. Lane applet. That's literally about 15%. And why do I know that? Because how do we get the standard deviation again? Great question, Ella. So we're going to take the original standard deviation of 5.60 divided by the square root of the sample size. Does that make sense, Ella? We take, so it's the original standard deviation right here, sigma, over the square root of n, which is the sample size right here. And we do 5.60 divided by the square root of 30, which square root of 30 is square root of sample size. And it gives us the new standard deviation for the distribution of the sample mean. And that's what this stands for, the standard deviation for the distribution of the sample mean. When we take samples of size 30, what variation would we expect in those samples? And yeah, great question. Keep asking those questions if you got them. This is a tougher problem. Like there's a few steps. And so we have the answer for the first one. Let's put in the answer. Oh my gosh. Hold that. So let's go out here. Can we not copy paste this? There we go. 4 decimals, check answer. Should be right. Woo, got scared there. The total amounts that he earns on his best 1% of such weekends is at least, now on the best 1% of weekends, this is where people usually get stuck, on the best 1% of weekends. So how do we look at this? Well, we need to take this same information right here. We're going to put in the mean, the standard deviation, and the best 1% of such weekends. Now, this is not how much he makes. This is his what tip. So fill in the blank right there. This is not how much he makes. This is his what tip. So this is not how much he makes. Like you wouldn't say I made $12.97.8. That would be your what tip. Because this is the distribution of the sample mean, so this is your what tip. That's not how much you make, because that would be not a great weekend. Not sure what to start for extrapolation of the multiple model. Oh, yes. Look at the X's and think about where you'd be extrapolating HCT. So where would you be extrapolating? Keep asking questions, HCT. Where would you be extrapolating? Like, just in general, where are you extrapolating? When you make predictions, where? It'd be the average. Yep. So since this is the average tip, we would see here that this is the average tip on 30 tables. I don't know why I can't click outside of that. The average tip on 30 tables, we take the average tip right here and we just multiply it by 30 for the best 1% of weekends. Hope you're... Oh, thank you so much, Forrest. That's awesome to hear. I appreciate that. So much positivity. I hope your day is going well too, Forrest. We're just chilling out, doing some work, having a great day. I appreciate that. If you have any questions, let us know. We just got one question done. Going to get the rest of these done and answer. HCT's got a bunch of great questions. Keep asking them, HCT. Let's see here. This question's very similar. This is a sample mean question right here. Let's just grab the start of it. I want to do the whole question. Let's do it. Okay. Open up some new word sheets this week. Okay. So with this question right here, let's first mark the notation. Remember, always mark your notation to begin with. We should know what each of these symbols mean. There's a mean right there. And here we are. Help me out by telling me one of the symbols. What is one of these symbols? It says carbon monoxide, CO2, emissions for certain kinds of car vary with a mean of 3.427 and a standard deviation of 0.8. A company has 80 of these cars in its fleet. Let Y bar represent the mean CO2 level for this company's fleet. What is one of these in notation? What is one of these in notation right here? What is one of them? Any one of them. Just having trouble calculate confidence rolls on? You bet. Which one are you working on for us? We'll do it right after this right here. We'll finish off this homework, and then we can definitely do that. Just put whatever question you're working on, and we can do that question for us. You got it. So be like, can you work this question, Brian? And we will solve that question. What are any of these in notation? Any of these right here. So knowing the exact notation is sometimes a little bit tough because sometimes people will call this the standard deviation. It is the standard deviation, but it's not going to be S. It's going to be sigma. Sigma stands for the population standard deviation. Number 3 on chapter. Yeah, let's do it next. You got it. You bet. You got it. We will do that. We're going to finish off this. I think there's 2 more in this. We'll finish this off for us, and we will do that next. So now that we know this right here, we know mu, which is the true mean. We know sigma, which is the true standard deviation, and we know the sample size right here. So with this, we're going to go right here and go mu y bar equals to mu. This is saying we expect the true mean of the sampling distribution to be equal to the true mean. Just saying if we have a whole bunch of cars on average, well, if the cars have 3.427, then we would expect 3.427. Next, we say the standard deviation for the distribution of the sample mean is going to be tighter because we're going to take it and divide it by the square root of n. So we just go right here and we take 0.8 and we divide by the square root of 80. There we go right there. And we take 80, we square root it, we copy it, we take 0.8, we divide by it, and we get 0.8944. Once again, we're going to go to David M. Lane for this. David M. Lane's going to help us out with our new mean and new standard deviation. Let's highlight those. These are our new means and our new standard deviations for the distribution of a sample size of 80. So we're going to go to David M. Lane. He's already up, but I'll put him in the chat right here. There's David. Oh, I did 2 exclamations. I do not know if that'll do it. Mubot might not like that. Mubot.
I am Mubot.
He didn't like that. So let's go right here and let's take a look. So we put in the new mean and the new standard deviation. 3.427. 3.427. My brain broke. 8.944. And I always put it in both of them because you might be using both. You never know. So in the first one, what's it ask? Oh, I think it asks what's the mean and the standard deviation. It's normally distributed. 3.427. That's the original mean right here. And the standard deviation, it wants to 3 decimals, so 8.94. Oh, what happened wrong? 0.8, normal model with a mean, a standard deviation. We must have made a mistake on the standard deviation. So 80 square root 0.8 divided by this. Oh my gosh. We did not add in a 0. That's not good. We probably did it on the David M. Lane also. Yep. There we go. Always double check your work. Did we write that down when we wrote it down? Oh, we didn't write that down. Good afternoon, Roger. Good to see you here. Ask any questions if you got them. I'm already making mistakes. Not good. Not good. Not carrying out all the answers. So we see right there, there's the new mean and the new standard deviation. Oh, I should have realized that it would obviously, when you divide by something, get smaller. I made it larger. So we have here, estimate the probability that the sample mean is between 3.5 and 3.6. We need to go over to the David M. Lane, which we're on, and we need to go between 3.5 and 3.6, which is going to be the button here. 3.5 to 3.6, and there it is. And if you notice, it's almost between there. It's going to be about 18%. Let's take our answer right here and go to 3 decimals. That'll round. The last one you can guess, which is really nice. The top 5%. The top 5% on the curve is going to be somewhere about... So the top 5% is going to be a z-score of 1.645, which is going to be about here. So it's going to be 3.6 when we round up. And you have to go over to this one, put in your numbers, and do top 5%. The top 5% should be right about there. So it's going to be at. Ready? Ah, it's over here a little bit more. And it rounds up to 3.6. Rounds up to 3.6. So here we are. Let's put in 3.6, the top 5%. Did not mean to put that 5 in. There we go. 2 more questions here. We got time, then we're going to do force questions. Oh, cool. I love that one. Okay. So with these right here, we have exploring the theoretical means. Now this question right here, we need to look at the formula to start here. This one seems super complicated, but I want you to see this formula. Here's the first formula we need to know. We get it on the test, but what does this mean? The mean for the distribution will be the true mean. The mean for the distribution of the sample mean will be the true mean. So if you look at this problem right here, we know that the mean is 36.23. So what mean would you expect in a sample of 2? We know that the mean is 36.23. So what mean would you expect in a sample of 2? If you took a sample of 2 and you know that the mean is this, what mean would you expect theoretically in a sample of 2? So I'm going to pause right here. I want someone to answer, because this one, once you see it, you're like, oh, but it's using the formula. That's where people get stuck. It's using this formula right here that if we know the true mean, because I'm telling you the true mean, so what would you expect to see in a sample of size 2, which is a mean for a sample size? If you took a mean of 2 observations and you know the true mean is this, what would you expect to see? Up right here is a simulation, which shows us what could happen, but theoretically, what would you expect to see? If the mean is 36.23 and you take a sample of size 2, what mean would you expect from that, theoretically speaking? So who knows? Take a moment. I want to see if someone gets it right here. We know the mean is 36.23. Hint. So we know the mean is 36.23. What would we expect to see in a sample? A sample of size 2. We know the mean is 36.23. So if we know the mean is 36.23 and we take a sample of size 2, what would we expect to see for a sample mean? Mewbot, you don't know the answer. What would we expect to see for a sample mean? What would we expect to see? If we know the mean is 36.23, what would we expect to see for a sample mean of size 2? If you have any questions, Roderick, let me know. We're going to do Forrest's question next right here. So we know the mean is 36.23. We know that is true. So since we know the mean is 36.23, what would we expect in a sample mean? This formula seems complicated, but we know the answer. We know this. We know the mean, because that's mu, is 36.23. So what's the answer to this right here? Hint, I promise this is not a trick question. And this might as well just be called x. We could just call that x right there. This is not a trick question. What is x going to be equal to? Because that's the mean for the distribution of the sample mean, and that's what we want to understand. We want to understand the mean for the distribution of the sample mean. It looks complicated, like you're multiplying things right here, but it's just a notation to say the mean for the distribution of the sample mean, which we could just call x. We could just say, this is what we want to know. And we want to know the mean for the distribution of the sample mean. So the answer is that. That is what it is, because it says it is what it is. Don't look at the simulation. The simulation is just showing you theoretically what could happen, not like theoretically like theoretical truth, but theoretical within randomness. Doesn't matter what the sample size is. Sample size is not used to calculate this. It's always going to be that. It's always going to be that. That's theoretically speaking, the mean for the distribution of the sample mean is going to be equal to the mean. So we always have that right there. Now, what changes is the standard deviation will get smaller, and you can see that right here in the simulations. The simulation shows it getting smaller, and we've been doing this today where we always take it and divide it by the square root of the sample size. So when you have a larger sample, it'll be smaller and tighter, and we always just take and divide by the square root of the sample size. So we can do the same thing right here with the standard deviation equation. Let's just draw it out. The standard deviation for the distribution of the sample mean is equal to the original standard deviation for the population over the square root of the sample size we are using. So it just gets smaller as we run it. And I think the first one was something like 3.99 over square root of 2. And that's all we're going to do is we're just going to keep changing this number right here to whatever it tells us. We're just going to be like, 2, then 5. And that'll just make it smaller and smaller and smaller as we do larger and larger sample sizes. So let's go right here and do 2 square root 3.99. I'm getting it from right here. And we divide by 2 square root 2.82. And it's kind of close to that. And then we go right here. Square root of 5. Copy paste. 3.99 divided by square root of 5, 1.78. And then we go next one, and we go 10 square root, and we go 3.99 divided by 1.26. Then we go 20 square root, 3.99 divided by 0.89. There we go. And so I think it asks about this, yes. Are the theoretical values close? Mm-hmm. Because it's simulation, so it should work. The theoretical values are very close. If you look at the numbers you just obtained, they are very close because simulations work, at least if we do them properly. Looking at the histograms, when do you think it'd be normal enough? Now, this one's tricky. I think this one uses 5. If you notice here, it's still got a little bit of an outlier. Here, it's looking pretty normal. Here, it's looking more normal at a sample size of 10. So as we see the sample size increase from 2 to 5 to 10 to 20, it's going to get tighter and more normal. Look how it starts out, and it goes from 28 to 44, and by the end, the distribution doesn't even go from 32 to 40, and you'd see right here. For extrapolation, would you say we begin extrapolating? Yeah, you could say one point where we begin extrapolating would be outside of this and outside of this. I wouldn't say a mean, and you can put your answer in the chat right here. HGT, if you want to put your answer in the chat or send it to me on Discord, I could look also. But I would say we begin extrapolating at this point, like I would say, outside of this and outside of this when we make predictions. Remember that extrapolation is when we make predictions. So I would say we begin extrapolating when we start making predictions using these sorts of X's. Like an extrapolation is always a matter of degree. Like when do we begin extrapolating when we're outside the bounds of the X's? So when do we begin extrapolating? Outside the bounds of the x's. The distribution of the original data, or is extrapolation at the min and the max, the values we choose? So for your summary, when you do a summary of your x's, like if you do a summary of your, it's my sample, right? You could do summary my sample the following way. Run this code right here. That should do it. That code right there, summary my sample minus the first column, that'll remove the y variable. And so then that will show you your x variables and the mins and the maxes to where you'd be extrapolating. Does that make sense, Roderick and HGT? Because extrapolating is making predictions outside the x's. So if we look at where our x's are bound, we might have some idea of when we'd be extrapolating. Does that make sense? The distribution of the original data, I think is pretty normal, it says, right? Or a little bit skewed. Well, do we have a... Or there it is. There's the original distribution. It's only a little bit skewed, so the sample size does not need to be that large. This is the large enough n condition. The more skewed it is, the larger n needs to be. And since it's not that skewed, great job, HCT. Yeah, keep asking questions. I'll keep answering them. And like the distribution is nearly unimodal and symmetric, so it does not take a very large sample size. So there we go. Last question, we're going to do Forrest's question and then 320, especially if you have questions, let me know. Using the t-table or software calculators, estimate the values asked for in the parts right here. Find the critical value for a 90% confidence interval with 17 degrees of freedom. Ooh, this is tricky. Whew. This is a tough one to do in your head. This would be funny. Darn it. We get 2 guesses. Okay. Let's find out the actual value here. One of my favorite applets for this, here I'll bring it up, is statdistributions.com. So statdistributions.com, I'll put this in the chat. Okay. I just actually sent this to my brother because he's doing statistics. And I'll show you this applet. So he's doing statistics and he said, hey, can you send me those applets again? And I was like, well, yeah, they're awesome. So we go over here to the T distribution. It's one of the buttons at the top. Just make sure you're on T, student T distribution. We put in 17 degrees of freedom, and then we need a 90% confidence interval. So 90%, let's do it like a confidence interval, and it's 1.74. Really? Really? Wow, I was way off today. There's the answer. I guess that's a good bit of degrees of freedom. Okay, we can get this one. We can get this one. Watch this. Boom. Got it. Good. Okay. How did we get that one right there? For that question, we're doing the same idea. I think it was 80-ish degrees of freedom or 81, and we do a 95% confidence interval, and it looks like we were close enough. It gave it to us with the plus or minus 1 the question might have on it. So we have the applet in the chat right now, 81 degrees of freedom, 95% confidence. That one has so much confidence or so many degrees of freedom that it's basically the same answer. So I was able to guesstimate this one right here. Can I do another version of it? Aw, darn it. We'll do one more version of it. I like guessing this one. It's probably one of my favorite questions of the whole semester because you don't... Here we go. 99% confidence, 12 degrees of freedom. Oh, that's so hard to guess. So 2.5758. I'm not going to get this one. That's such a hard one to guess. 12 degrees of freedom, 99% confidence. So 12 degrees of freedom, 99% confidence. 3.05 or 3.06 when you round it. That's a hard one to guess. And 72 degrees of freedom, 2.34. Should be right. Really? 2.3263? There we go. So close. 72 degrees of freedom, 98% confidence. And, oh, wow. 2.38? Wow, that's a wide margin of error. Last try, then we're doing Forrest's question here, just because I love doing these questions. It's just, when you understand how the degrees of freedom work, you can make some pretty good educated guesses on these. See, look. There we go. And 62 degrees of freedom. So, wow. There we go. And this can be done in the applet right here, but generally speaking, wish I got them both first try, but there we go. 2.66 right there, and I was really close with that. So just know how to use the applets, understand what they're showing you, and please note that I'm doing a confidence interval here because the areas between, like if we go to somewhere like a 90% confidence, and then we put in the degrees of freedom, and we could talk more, especially in class. We do talk today, starting with William Gaussian degrees of freedom. Would it be easily understood if we extrapolated beyond 1.5 and 34? We'd have to specify, well, which variable are you talking about, HGT? Which variable are you talking? Because you're saying extrapolating beyond 1.5 or 34. Like if you say that to me as a person hearing your problem, I'd want to know which variable are you talking about extrapolating on. I think you're talking about average temp, right? So make sure to give that context, always context. Remember, all data needs context. 201, we review that. You got it. So I think you're talking about average temp. I think. I could be wrong. Let's go here to Forrest had a question on confidence intervals homework. And 320, feel free. We can start doing a bunch of 320 here. Question 3, I think it was. Forrest had this question. The potential donor mailing list. So we need to work this question right here. Average wind speed. There we go. Yep. So make sure to say, leaving the bounds of 1.5, 34 miles per hour. Really? I got to see this. Doing so much R work. Okay. So we use I have to look at this real quick. Is it really that far? Well, I'll be. You are right, HDT. It is, you are extrapolating outside of this bounds right here. That is pretty crazy, 34 miles per hour. It's weird that it's average wind speed, so it's like average across the day. 34 miles per hour, it sounds like there was a hurricane that day. You also notice it's a bit of an extreme value right there. So, I mean, that is a bit of an extreme value, but that would be an extrapolation on that day, right? Or outside of these bounds. Also, weird combination of the X's would be extrapolations too. Like in the multivariate sense, you're extrapolating when you leave the X bounds of the model. Does that make sense, HGT? You are correct. And identifying these as the bounds for your lower bound for extrapolation and these as the bounds for your upper bound for extrapolation, at least in the univariate X sense. In the multivariate X sense, the pairs command will let you see that. So the pairs command is going to give you an idea of the multivariate. Yes, great job. So we need to have an understand what a univariate extrapolation is and a multivariate extrapolation, because there might be unusual combinations of X's that would be multivariate extrapolations. So, but that's the univariate extrapolation. That's still extrapolating to be outside the bounds of an X variable. But then are we in the multivariate extrapolation? Oh my gosh, it gets so complex. Multiple variables, everything gets crazy. So let's copy down the notation for this. Okay, so we need to mark our notation. We always mark the notation. So Forrest, if you're still here, what is the notation for this? What is the notation? So let's go ahead and grab our pen, start highlighting stuff, and see what we have. We have this, and we have this, and we have this. So the formula we are using is going to be p hat plus or minus z star, which means we get to pick the percent confidence, which we have. And then we go p hat q hat over n square root. It's a great problem to practice your notation on, because you have to find 5 things. 1, 2, 3, 4. 4 things. 4 things, and you're given very little of what you need, or at least to start. This is going to be relative to the z-score. This is the sample size. This is the amount of successes. So from here, we need to solve for certain things like p hat. P hat is the sample proportion, so p hat is equal to x over n. So we just go right here and we get 5466 over 100,000. That's going to be equal to 0.05466. And as soon as we have p hat, we're going to take q hat right here, which is just 1 minus p hat. And that should be 0.9453. 34. Let's find out how good Brian is at mental math. 1 minus 0.5446, 94534. Good deal. We have it. Now we have Q hat, we have P hat, but we need the Z-score. Now the Z-score, because we've used the applet a lot, is going to be 1.6449. It's going to round that to 5, though. So let's bring up David M. Lane, as per usual. My hair is getting in my face. So we have here David M. Lane's about to show up, but I think we have it on our taskbar already for today. We do. So we're going to go here, and we need to put in Z-scores now. We're going to bring this back to Z-scores, which is a mean of 0 and a standard deviation of 1. Hey, David M. Lane in the chat. And now we need to do the middle 90%. And we can confirm it by looking up here and saying that is the middle 90%, which is a confidence interval. And we have 1.645, which is the Z-score 1.64499. I believe it's 4499. Got another 9 after it. So just, you got to be super decimal place. You don't have to be that accurate. Someone's going to be like, do we really have to be that accurate? And I'm like, no. Brian's crazy. He carries out way too many decimals when he does his mathematics. Carry them all out, every single decimal to the 10 billionth decimal and beyond. So P hat is 0.05466 plus or minus the Z-score of 1.64499. And then we do square root 0.05466 times 0.94534 over 100,000. So there we go. We got our P hat, Q hat over n square root. Let's go ahead and solve this out right here. We're going to solve out the margin of error first. So we're just going to take this, multiply it by 0.05466, divided by 0, 1, 2, 3. There we go. Square root that. And of course, scientific notation. 0.007188. Oh, we didn't multiply it by 1.64499? 1.64499. There we go, out of scientific notation. We could have done it either way. 0.00118. I think that's right. And then we just plus or minus. So now we're just going to take this and add and subtract it. And 0.5466. Let's go back. And so we go this. And let's times it by 100. That's just going to turn it into a percentage. And then 5.466 plus this. So that's 5.58. And let's take, we're just doing this as a decimal, 5.466. That's just it as a decimal. And then minus the margin of error, 5.35. Let's just explain briefly what we did right there. We just turned these both into percentages. So we're just adding and subtracting a percentage right here, 5.466 plus or minus 0.118. Both of these were just times by 100 because it wanted it as a percentage. That's all we did right there. And then we're just adding and subtracting these numbers so that we can get plus the margin of error minus the margin of error. And when you add this value, you obtain the following, 5.58. When you subtract the margin of error, you obtain the following, 5.35. So we're just adding and subtracting the margin of error, which you can see right here. So we go 5.466 plus this, and we get the 5.57 or so. And then we subtract it, and we get the 5.35. So we're just adding and subtracting the margin of error. And given the confidence interval is 5.3 possible, you might be like, well, it's kind of close, but no. According to our interval, no. I mean, it's possible, but not really plausible. So we would say no, right here it's outside the interval, and that's not really plausible. That's got it. Good stuff. 98% confidence, just to speak briefly about this one. If you have 98% confidence, you would just change this right here, and you'd get 2.3263. There we go, 2.3263. So you don't have to memorize the z-scores. We will give them to you on the test. But you should know the z-score is bigger for this one because going from 90% to 98% confidence, you're going to cover more of the curve. So you do have to have understandings like that. We don't expect people to memorize z-scores, but we expect you to have an understanding. HGT and Roderick, what questions are there? What questions are there? I think, what do we have? Who has questions? We've hit a lull in the class. Yeah, the z-score. So make sure to go to the David M. Lane, and anytime you need a z-score, like let's say you go to a problem right here. This one doesn't have you do z-scores. But whenever you need a z-score, go to David M. Lane, and you just plug in the numbers with the mean and the standard deviation. If you need a 95, there's the 95 z-score, 98, 99. Great job, Forrest, right there. That you're welcome, HTT. What else are you wondering about? We got like 14 more minutes. I think. I can't remember if this is an hour and a half or hour. I'll probably go answer some emails after this. I'm not caught up on emails yet. I need to catch up on the emails. The emails. So many emails. We got this though. Let me see. Google Calendar. Google Calendar. Oh no, we go to 1:30. Go right up until class. Can you go into number 4? Yeah, of course. Yeah, Forrest, definitely. Let's do it. Thank you for being here, Forrest, and thank you for working out the problems. Let's work on this one right here. Okay, what's the first thing we're always going to do, Forrest? What's the first thing we identify when working on a problem? Anytime we're working on a problem, what do we identify? And you can always, if we're working on a question now, you can always ask a question and then I'll get to it. So sometimes people wait till I'm done with a question, but no, just drop a question in. So if you're watching right now, be like, hey, Brian, can you explain this or can you go over this? I am more than happy to. It lines up the next question. Forrest had all his questions ready and we just were hopping into them. And there it is right there. You're welcome, Zoya. Thank you for being here, Zoya. Let's throw out some 50 points to the chat. So thank you, Zoya, for being here. I appreciate it. So what do we have notation-wise right here, Forrest? What do we have notation-wise? Let's identify. I'm going to start writing the equation. So we first identify the notation. And what do we have notation-wise right here? Exactly. And so do you see any of them on the screen to identify? It's talking about a study where they took 2,400 children. 24% of them have vitamin D deficiencies. We want to make a 98% confidence interval. If you start us off with any of these, I'll fill out the rest of them. Z-score samples. Nice job, Forrest. Excellent work. That's worth another 50 points. Great job. And so one other thing we can get, which you did perfect right there, we can also get Q hat. It didn't give us Q hat, but from this we can get Q hat. So let's go right here. That is P hat is equal to 0.24. As soon as we find P hat, we're going to find Q hat. Q hat is 0.76. Sample size right here is N, and this is the Z-score. Now we're going to go to the David M. Lane. We'll put that in the chat here again so anyone watching the video can be like, oh, that's the most recent link that they just posted right there. So the David M. Lane is going to bring us to the following site, and we're going to use the Z-scores of 0 and 1 on the second button. Make sure you're on the second button, and we're going to go right here. Could you go over the catalog question on? Yeah, of course. Question 13, catalog. Is that on the homework or the quiz, Jordan? Feel free to tell us which one, and then we'll do it. 2.3263, there it is right there. Good to see her, Caitlin. And good to see her, Jordan, too. So the Z-score is 2.3263. You know what I'm going to do? I'm going to double check. I want to see it. 2.3263. I am correct. And then there's a 4 after that. Cool. 2.3263. Just quiz. You got it. Oh, and for the quiz, yeah. Put the start of the question in there, Jordan. And because the quizzes change. You're welcome, Caitlin. Glad people are working away. It's Monday morning. People woke up and they're like, it's time to work. It's time to work. We got this. I mean, it's 1 p.m. in Knoxville. It's 1:50, but I mean, still. Maybe someone's waking up right now. Someone woke up right now. Someone just got out of bed. They're like, it's time to work on statistics. We got this. Like it's almost 2 p.m. They say, yeah, I was working hard this weekend. We're just plugging in the numbers right here. We're going to solve the margin of error first. Got to put in the right thing there. There we go. So 24% plus or minus all of this down below. So now we're just going to solve this out. I always solve for the margin of error first. So we're going to solve this portion right here, 0.24 times 0.76. There's the top part. We're going to divide by the bottom part. There we go. We're going to square root it next. Let's go ahead and square root it. Now we're going to times by this right here, multiplied by 2.3263. Got it. That is the margin of error right here. So with the margin of error was 0.24 plus or minus almost exactly 2%. That was way too much. It was like 2.02. Yeah, if you do it as percent. Rounds to a 3. Darn. There we go. So now that we have this, let's see how it wants it entered in. Let's go back here. Round to 3 decimals. Okay. So if we go right here, and it was it was that right there. We're going to take this and subtract. All we're doing, so that's, oh my gosh, my brain's breaking. That'd be 22. Is it really going to be, when you round it, can we just do that? I don't know, it's going to have a problem, isn't it? No, it rounds to that. Yeah. With everything rounded, and this one turned out so nice, rounding to 3 decimals, you just get this, and then you can delete this right here. So this one's really easy. We got a really nice one, at least when it comes to rounding, is 24% plus or minus 2%. So especially if you're wondering, how am I getting these final numbers right here? All I'm doing is just taking and adding in 24%. So you just go both times on it. You just go right here and do the first way. When you go right here and you say 24%, you just do it as percent plus 2% equals to 26%. 24% minus 2% equals 24%. Doesn't want it as a percent, wants it as a decimal, but I like talking percents a lot more. So you can see the answers we obtain right here are just the plus or minus. So you have to go plus or minus on this and add and subtract that 2%. So 24% plus 2%, 24% minus 2%. Oh my gosh. What have we done right here? There we go. Now we got the right answer. Someone in the video, someone would point that out. Someone would be like, what are you doing? How are you teaching mathematics and you can't do mathematics? I can do the hard questions in my head. I can't do the easy ones. Can't add and subtract numbers. So I would interpret this, we are 98% confident the true proportion of children who are deficient in vitamin D is contained in the interval. So we are confident, 98%, that the true proportion of children who are deficient in vitamin D is contained in the interval. So what does it mean to make confidence rolls like this? Can I get that displaying on the screen so we can see it? I'll vanish. About 98% of random samples will produce confidence intervals, because we're saying we would get confidence rolls. You're welcome anytime for us that will contain the true proportion. That's the point of a confidence roll, is contain the true proportion estimating from a sample. That's got it. And I think we have Jordan's question next. Jordan said, could we go over the catalog sales on chapter 13 catalog sales question? Let's check that out. Catalog sales question. Great job. My Pearson. A lot of my Pearson this morning. A little 320 interspersed. Catalog sales quiz question. Where is it? Whoa. A lot of questions. Oh, here it is. It might have been this one, though. I think usually this one is just the interpretation of interval. So one can be 95% confident, or 95% that the true proportion. I am 95% confident that the true proportion of people who place the order on will get their order within 3 days is contained in the interval blank to blank. That's the interpretation of this interval with the margin of error in the center, which comes from the sample. So this one right here is the more difficult version, though, where it asks a lot more kind of in-depth questions on it. Off to Spanish class. Me gusta español mucho. Adios. Till tomorrow. Hasta luego. It might be hasta luego. So, my Spanish used to be way better. Muchos años pasado. I need to study español more. For model hierarchy, would an explanation be the linear model retains model hierarchy because the individual estimates for each variable remain within the model? Exactly, for x1 and x2. So if you do maintain model hierarchy, it's because if you have x1, x2 interaction, you need to have x1, x2. Does that make sense, HGT? If you have x1, x2 interaction, then you need to have x1, x2. Does that make sense? So the linear, or you wouldn't really call it linear model, you just might say our model, because it's not really a linear model anymore. Would you say my model maintains model hierarchy because I have the interaction and I also have the x1, x2 variable. So if you have x1, x2 interaction, you need x1 and x2. Great job, great job. So between 77 to 84% of all orders arrive on time, because we're looking at this interval right here. The interval estimates that the true proportion of orders that will arrive on time is centered at 81% plus or minus 7%. So what does this mean? Oh, that doesn't give any confidence. So we don't want to do that. This is the interval itself with the plus or minus. This interval implies certainty. We need confidence. I am blank percent confident. 95% of all random samples of customers will show that 81% of orders arrive on time. No, that sounds wrong. There it is. 95% of all random samples of customers will show. No. This is way off. It would not be. I want to get it on the screen. There we go. It'd be way less than that because you're going to see this occur that it doesn't even give the interval. This is a horrible answer right here because we would say I am 95% confident that the true proportion of orders that arrive on time is contained in the interval blank to blank, or the true proportion of people who get their orders within 3 days. So this is not correct. Much less than 95% of people or the random samples will get the order 81% on time. One can be 95% confident that the true proportion, this might be right. I am 95% confident the true proportion of orders that arrive within 3 days is between blank and blank. That sounds correct. That sounds very correct. Watch out, they change this up. You might not have one that is correct. But this sounds like I am blank percent confident that the true blank that will arrive on time is contained in the interval blank to blank. That sounds very correct. Our way of writing it, let me write it out. The format I use is I am blank percent confident that the true blank there you go is contained in the interval blank to blank. I am blank percent confident that the true blank is contained in the interval blank to blank. So this is what we need to do right here. If we see something like it, it looks correct. I am 95% confident that the true proportion of orders that arrive on time within 3 days is contained in the interval blank to blank. And if you look at what they wrote, I am blank percent confident that the true blank is contained in the interval blank to blank. Very correct, it looks like. Now, this might look like it to you too, but one can be 95% sure. Okay, that's similar enough. We can let that pass. That between 74 to 88% of the orders placed by the sample per customers, now that's the issue. The sample customers, no. The true. How do you tell what causes a multiple exponent not be to explain? That's a really good question, HGT. Let's do that next right here. Yeah, Hannah, you're welcome. So we're not estimating for the sample customers, and we actually know the truth for the sample customers. If you remember from all these intervals we've been creating today, the center of every interval is p hat. So we actually know p hat. We know the answer for the sample customers. So the center of every interval here, which is 0.24 for this one, is p hat. So we know the answer for the sample customers. So this is not correct. In the sample 81%, that's p hat right there. We know the answer for the sample customers. So we know that. There's a 95% chance on a given day. That doesn't sound like true proportion. I am blank percent confident that the true blank. No, we're not talking about given days right here. So this statement is not correct. The confidence interval is an interval to estimate. No. The 95% confidence refers to the probability of the interval containing the population proportion. We should have it all correct. Woo, we got it. That's a good tricky one. How do you tell what causes a multiple model X variable to be not significant, and does that need to be explained? Oh, really good question, HGT. Let's go over HGT's question right here. I'm going to make a crazy model, HGT. So you ready for this? So here we go. Watch this. Cool. Check out this model. You're welcome, Jordan. Great job, Jordan. Let's throw out some 50 points. Thank you, everyone who's watching right here and practicing along and doing assignments. We've done a lot of my Pearson Day already. So throw out some 50 points to everybody. Thank you, Jordan. Great job. Already in the Hall of Fame. Nice job. You're almost near the next level, Jordan. When you look at this model right here, what is significant in this model? How many variables are significant? This is not a horrible model. This might be the best model. I don't know. We could look at it. I'm actually looking into new R packages, some new stuff. I'm trying to increase what we're doing using some new latest, like better and better things. Like what is the latest and greatest things we can use? there are two significant variables. Now, interactions are built from if you see, here's all the interactions right here. The code I wrote had the twiddle dot, and then it had raised to the second. So this is all the two-way interactions. So this code right here does all two-way interactions. And what do I mean by two-way interactions? Interactions between two variables. Like here's an interaction between two variables. You can do interactions between three variables. And here's all the three-way variable interactions. So now we get a few more significant variables. Intercept's not significant. No one cares about the intercept. But here's all the three-way interactions. Does it make sense what like these are interaction variables right here, where you have the interaction between effective average temperature, or average humidity, and average wind speed. There's only one four-way interaction, and there it is down here, which it's almost significant, which is weird. And we're starting to see more dips in the R-squared adjusted. I don't know if this model should be used. Who knows? But does this make sense, what you're seeing right here, HTT, like with all these p-values and everything? Do we need more room? Finally, it prints on the screen. There we go. So behind me right here are all the p-values in a four-way interaction model. So does this make sense right here? You've got some that are significant, some that are not, and this is ridiculous. Like four-way interactions are just absolute insanity. And it's really interesting to me that some of the three-way interactions are significant. So I don't know, maybe we need to consider this. Who knows? Who knows what the truth is? All models are wrong. This model's wrong. Every model's wrong, but some are useful. So why do you think like things like average temperature here and effective average temperature are really not that significant? What do you think is happening, HDT, to subtract from the ability to find significance? Because all of these interactions are built from the variables in the model. So what is happening right here with all of these interactions that's probably damaging the ability for them to find significance? This is a key concept right here, and frankly, I would just put this as a test question, and there should be one big answer that jumps out immediately that we can immediately investigate. But why do you think there's a big issue with finding significance for these variables and things that are no longer significant right here? There's a few ways to answer it, but it's the idea of a multiple world, and why in this four-way interaction model are we seeing things that are not significant? They're explained by other variables or interactions, exactly. And so where would we see that? What key words would you put in here? There's some key phrases I would, if I'm writing this as like, if I'm going to explain the answer, I would want to make sure the teacher knows that I know that this is like the word I'm alluding to, which what you've done right there is really great because you didn't use statistical terms and I know what you mean. Like I know which statistical term you should be going towards. So maybe this is now maybe it says like what statistical word explains this concept right here. Maybe that's what the question says. Like what statistical word would you use? Of course, then we need to know, like, we can't just say that word. We have to then explain what it means, which you've done right there. Like you've said that the X's have overlapping variation in what they're explaining. So this would be called So the interactions are going to have multi-collinearity, which means they overlap in what they do. They're going to overlap in their variation. And the multi-collinearity is going to show up in the variance inflation factor. And whoo, that's some variance inflation right there. These are insane. Our cutoff for high variance inflation is almost 2. It's like 2.1 or something. So 1 over 1 minus r squared of the model, 2.04. 2.04 is considered high variance inflation. Our variance inflation factors are up towards 45,000, 71,000. Do you know when a variable just has bad data? Yeah. How would we investigate? That's a great question too. How could we investigate if a variable has bad data in it? Like how could we investigate if a variable, like let's say we want to look at this variable right here and see if it has no information in it just by itself. What would we need to do to see if this variable by itself has no information in it? Really great question here too. Like how would you investigate if this just is a bad variable that doesn't bring any information by itself? If we want to see if it's a bad variable by itself, we have to make the simple model. So this variable that was not significant in the multiple world is significant by itself. We could visualize it to kind of, that's a good answer too, but we do want to find the p-value of it in the simple world to see if the variable by itself has information. So do you see how this variable by itself has information, this three-way interaction by itself, and we have violated model hierarchy here because you'd need all the two-way interactions and all the simple terms that go into this. This is a model that violates model hierarchy, but it does show that the three-way interaction does have statistical significance. Does that make sense here to say that the three-way interaction is statistically significant, but in the multiple world, probably due to multicollinearity, it is not statistically significant anymore. So the three-way, oh, you can't see it behind right there. So the three-way interaction right here in the multiple world is not significant, probably due to the large amounts of multicollinearity, which shows up in the variance inflation factors. We definitely have crazy high variance inflation factor found by our cutoff here, 1 over 1 minus r squared of the model, gives us the cutoff for high variance inflation factor. Some literature will say it's high if it's higher than 5 or 10. We make a model-dependent variance inflation factor, which you can always kind of remember 5 or 10 is kind of high, but these are ridiculous. This is absolute insanity. And so we can investigate the significance of it by itself by looking at the simple world. And the simple world tells us the variable by itself, whether or not it is statistically significant. And this variable by itself is very, very, very statistically significant. Like, very, very. I'd say very, very. Two varies. That's a very small p-value. So, yeah. How's it looking, HGT? Great answers, great questions today. If you have more questions, let me know. Oh, it's Monday. We're in like the last full month of school. I can't believe it. And then summer. I'm already looking at summer classes, getting them ready. Much better. That's great to hear. It's just sometimes you got to review these topics. You got to go over like, what's it mean for something to have significance in the multiple world, the simple world? What's variance inflation factor mean? What's multicollinearity mean? And these are just concepts we need to know about how regression works. So great job. Coffee, coffee, coffee. Look at that influence plot right here. That's not good. Ooh, I wonder what we got with this. Oh, wait, let's go back to our multiple model. What is this influence plot going to look like? Ooh, we got some stuff that, hey, Adam, good to see you here. We have nothing with undue influence. This model right here does not have variables that are putting out undue influence on it. We have a very high, like, why does this point right here not have undue influence? At least, I don't know. It's a lot of influence, but the size of the circle is the size of the influence. This model is extreme in its values of the x's, but the model is actually predicting it pretty well. And by pretty well, I mean, it's a little bit off, but not far enough off that we see a big enough influence. I mean, these 2 points are a bit worrisome, but there are some other points with some moderate influence, larger influence, but nothing in our danger zones. We should know right here that this is the extreme for a high deleted studentized residual with extreme leverage because it's beyond the high leverage point. And once down here is the extreme deleted studentized residual loci that were down here. And then also this is extreme leverage, which means extreme in its values of x's. Just think about leverage like a tilting thing, and how far you are away from the mean of the x's is your leverage. So the further out you go on this board, you'd have more leverage over here. So we don't want high leverage because high leverage can lead to high influence when you put high leverage together with a high deleted studentized residual. Deleted studentized residual is just how far the model misses it when we remove the influence. That's what the deleted part is. And we go over that in class, and we did it last week too, but whatever people want me to cover, we can cover right now. Or where like someone's, yeah, it was pretty good. Good Easter. We had a good Easter. We had our bunny celebrate Easter with us. Do I have those pictures? I'll show a picture. Everyone always wants to see pictures of Bun on stream. He's our Easter bunny. No, I should post it. He's such a good Easter bunny. Maybe I'll show that. Maybe I'll get that ready for class so people can see like Easter bunny. And so like, yeah, and to whatever holidays people celebrate, happy. What holidays are there? So if I'm forgetting, I'm just thinking what holidays are there. Like whatever holiday you celebrate, I just want to say happy. I'm just thinking what is. I'm sorry. But I always want to let people know I think there's another one. Calendar of holidays. Let's see right here. Oh, found something. Holiday Insight. Please don't be a bad random site. Okay, wait, here we go. We are. I even forgot what month we're in right now. Ramadan's beginning. Ramadan begins very soon. Happy Ramadan to people, to everyone. And Ramadan's interesting because it moves. 10 years ago, oh my gosh. I had a roommate who celebrated Ramadan, and it was more during the summer then, but Ramadan moves every year. It slightly shifts over earlier in the year, I believe. So, National Walk to Work Day. So happy Ramadan to everyone who celebrates Ramadan. But yes. Do you remember if we've gone over task 2? Ask anything you want to know, and then we can go over that. You got it. For sampling distribution of a sample mean, the conditions are a random 10% and what else? The third condition, Maddie, great question right there, is going to be the nearly normal large enough n condition. So the nearly normal large enough n condition. So what is the first thing we do to check the nearly normal large enough n condition? And so this is a great review for the test. I'm always trying to do a little bit of a teach to the test every once in a while. What is the first thing we do, and how could we do that? Hopefully you can read my scribble right there. So what is the first thing we do? I feel like there's another holiday that we just passed, and that holiday list was not the best. Didn't have everything on there. What is the first thing we do, Maddie? And how can we do that? And this is a great review for the test, because I know what's on the test. If you know this, you might get a question right on the test. So we sometimes do a little, I just need some help with the code. Yeah. Whichever part you're on, feel free to ask. Be like, can you explain this? Can you explain that? Whichever thing you want me to explain, Adam, just let me know. Just be like, can you explain this? And so what is the first thing we do, Maddie, to see if it's nearly normal large enough n? And it kind of goes back to this. Where's the picture at? Here we go. This right here. So the first thing we're going to do is we're going to look at the shape. So if you saw this right here, like you could look at the histogram, and that's what I have right here is one way of doing that is looking at the histogram, look at the normal probability plot, or look at the goodness of fit test. These are all quantitative ways of describing data. So when you look at the shape, how does that look to you? The answer's up top, but how does that look to you right there? So if this were on a test, it would probably say this looks what? Like if it were to tell you in words, because sometimes we don't show it, we just say the distribution for people's weights are this, blankly distributed. So this one would look very, very what? How does that one look? So this is how to check the nearly normal large enough n condition. So it should, yeah, you bet. Let's do that next. You got that, Adam. We'll create the model with the interactions and the main effects. You got it. So we're going to see if n is large enough here by looking at the shape. What does the shape of this one look like right now? What does the shape of that one look like? So the shape of this one up top right there looks to be normal. So since that shape up here looks to be normal, let's do a sample of size 2. So we're going to go here to a sample of size 2. And that means we're going to take the mean of 2 observations. Look how it takes the mean of these 2 black dots right here. And then we go right here and we create a distribution of the mean of size 2. And we get a new standard deviation that's tighter than the original one, but the mean is still the same. But did we pass the nearly normal large enough n condition? And what does it mean? It says to us that if n is large enough, the new distribution will be nearly normal. So I want you to look at this real quick. Does this look nearly normal? And the answer is yes. That means n was large enough. So how large did n need to be? Since it was normal, we needed a sample size of at least 1. So since it was normal, we needed at least 1. And we have that right here. We have at least 1. But Maddie, now let's use this one, which looks skewed. So now we're doing the distribution of the sample mean of size 2, so it's taking 2 dots and doing the mean of those 2 dots. So will this sample size right here be large enough that the new distribution will be nearly normal, yes or no? And Adam, feel free to answer too. But if I keep doing this and look at the distribution of the sample mean, will the new distribution down here with a mean of size, or a sample mean of size 2, will that be a large enough sample size if the original distribution is skewed by looking at the histogram or normal probability plot or goodness of fit test to see how normal it is? So is there this n right here large enough for the new distribution to be nearly normal? is it large enough? Because it's skewed. So this is skewed. And so we have to look here at this. And then we have to look at this. And then we have to say, is that large enough? Is 2 large enough for the new distribution to be nearly normal? It is skewed, and we're using a sample size of 2. So is our sample size large enough such that we meet this condition right here? And the answer is no. It is not large enough. And what does that mean? It means that the distribution won't be nearly normal. And take a look, it's not nearly normal. So that's what we're saying when we say, is it exactly HTT? You got it. So this is not going to be nearly normal. But what do I need to do if it's more skewed? We need a water n. We need a water n if it's not nearly normal. I mean, if it doesn't meet the condition because it's skewed, the more skewed it is, the water n needs you need. This is the whole idea of like understanding what it means when we say like it'll be nearly normal if we have a blank enough n. So if it's more skewed, we need a larger n. And so why not go right here, exactly larger sample size, and that means we're going to average together 25, and that's large enough to meet the condition with just the idea that if it's skewed, and take a look, now it's nearly normal, and it's also tighter because it states, the central limit theorem states that it'll become more normal and tighter the larger n is. I wish this went up to 100. Do I have that on here? I had a central limit theorem applet. I don't even know what this applet is. What is this? Well, that's weird. I've got some sort of file on here. Oh, that's interesting. I don't know where it's at. I've created so many. You're welcome. This really helped. Oh, that's awesome. Nice job. Good luck on the embroidering. Definitely let us know how it goes. So let's go right here and create a model with interaction terms. Let's go right here to average temp. These might be the two. I can't remember. Average wind speed not found. How do we spell average wind speed? AVGO, lowercase s. Oop, there we go. Graphical error no one cares about. There we go. Oh, nice job, Caitlin. Yeah. That's my goal, is like working through and understanding. There's a lot of overlap between what we do in different classes, like understanding and working on problems is the way, like, I love it because there's so much bridging the gaps between like 201, 320, 474, 475. It's like practice. So right here, we have the model. Oh, man. There we go. Now we'll start to see it. There we go. Got to make it really small. Sure. Ooh, that's like no interaction. We'll be going over interactions more today and tomorrow. There we go. So if you notice right here, what's interesting about interactions is the interactions are the idea of it depends. So the coefficient of average temperature depends on the coefficient of average wind speed. When there's a higher, so when we talk about average temperature's coefficient, when there's a higher average wind speed, so for wind speeds that are large, you see here that there's a steeper slope. It's a little hard to see right there, but you notice the lines start out more apart and then they approach each other because this red line has the greater slope. But this is actually not statistically significant, but this is creating, does this make sense right here, Adam? This right here creates the model with the interaction term. So when you see an interaction term right here, the coefficient of average temperature depends on the coefficient of average wind speed. When average wind speed is larger, and you can see right here the positive coefficient, it's going to make a stronger coefficient. But it's reversed right here because this starts out with a negative coefficient. So the average wind speed coefficient also depends on the average temperature coefficient. When average temperature has a larger coefficient, it's actually going to be weaker. It's hard to see that. Let's create an interaction model where we actually can see the significance. Do I have survey 11 in here? Survey 10? Favorite survey 10. Survey 10. So let's go right here and do the interaction of weight and desired weight. Might be spelled like that. And predict someone's height. Height not found. Okay, good. We got it. Does this... it's stronger. No interaction right there. The interaction right there is super weak. That's as weak of an interaction as you can get. I mean, okay, it can go up to 1, but that's still really weak. Trying to find a good interaction. I don't. It's better. What do we have here that could interact with it? Trying to find a good interaction. I wonder. You know what? Desired weight with athletic then. Let's predict someone's weight. I mean, it is significant. Good. I found something significant right there. Maybe I'll explain why I thought this would be something. Trying to find significant interaction. I mean, yeah, that's pretty good interaction. So we're trying to predict people's weight. And if you know how athletic someone thinks someone is, like how athletic someone thinks they are, then that would change. So let's look at this right here. Okay, cool. I want to make it so it's readable. Okay, visualize model. There we go. Okay. So if you're trying to predict someone's weight, knowing how athletic they think they are, like these are the people who think they're more athletic, knowing their desired weight would predict their weight. And you can see right here, it's a weaker interaction right here. So when someone has a desired weight that's higher, would I need VIFs to say that there's high? Exactly, yep. You need VIFs to say there's high multicollinearity, and interaction models usually have high VIFs. I'm just trying to find a really crazy strong interaction right here. I'm trying to find something that just like, I want to find something that's ridiculous, which I just can't find right now. It's much easier to explain interaction when it's really strong. Hair is just getting way too long. Satisfied with weight. Woo, that'll be interesting. Let's go right here. It's a categorical variable, but let me just attach it. Make life easy by attaching it. Do the things we shouldn't do. Let's predict somebody's weight from their height and the interaction with satisfied with their weight. Really? Okay, I thought we found a high p-value before, but really? That's as weak of an interaction as you can get, and those lines are almost perfectly parallel. Wow. Okay, I'm bad at finding interactions today. That is a horrible interaction. Like, that's nothing. We're trying to predict people's weights. Smoker, maybe? Too large. It's fine. Really weak interactions. Let me do a quantitative one also. GPA, why not? Why not? Wait. Let me close off this data set. Do you have GPA on? Oh, you got GPA. Good. Just can't find strong interactions today. Oh, but nah, it's not strong enough. Even though that line is ridiculous. Man. We're just getting weak interactions everywhere. Can't find strong interactions. Interaction variables, where you at? My gosh. Okay, let's go back to the original problem. I'm gonna try one more time right here. Try to find these interaction terms. Attach mass sample. There we go. Demand tilde. Actually, you know what? Yeah, I don't know. I don't want it. That'll work. Okay, we'll do it the right way. You always want to put like the data frame you're working with right here. Just not strong interactions. Yeah, okay, that's a ridiculous interaction. Okay, cool. Whoa. Yeah, that's wow. So, especially when you look at this one right here, it's probably one I'll use in class today. If you look at this plot right here, when average temperature is high, effective average temperature has a negative coefficient. When average temperature is low, effective average temperature has a positive coefficient. I mean, that's huge. So the larger the coefficient, or the larger the value of average temperature, the weaker and then more negative the coefficient of effective average temperature. So effective average temperature should have a positive coefficient to start, positive coefficient, and then it should go more negative to end. So let's see that right here in the summary. Let's go here to a summary of our model. And we should see effective average temperature having a positive coefficient with a strong negative interaction. And I put test questions like this that have you figure that out. We see here the positive coefficient to start and the negative interaction, which is going to cause it to be more negative. So you should be able to kind of deduce these things by looking at this to see for small values of average temp, there's a positive coefficient, which means effective average temperature would have to start out with a positive coefficient, but as average temperature gets larger, and here's the negative interaction, as average temperature gets larger, we're going to see it eventually get negative for very high values of average temperature because this is the interaction causing it to be more negative. So the coefficient of effective average temperature depends on average temperature. That's what this means right here. The coefficient of effective average temperature depends on average temperature. When average temperature is small, it's going to have a positive coefficient, but the larger it gets, it's going to get weaker to the point at which it eventually becomes negative. So hopefully this is making sense. But yes, that's how we interpret interactions. Let's hop to space. Hold on, do we have music? Make sure music is playing today. I just clicked Photoshop. We don't have music. Let's put on music. Photoshop, we don't need you. It's opening. Takes a while to open. But that's got it for now. We'll head off here. Get a little food before class. You're welcome, Adam. Great job. Glad it helped. I'm going to head off, grab some food, watch my background break, and we will be back later. Bye for now, everyone. Bye.